Hello, in today's video, we are going to be taking a look at LeChatelier's principle, which deals with if a system at equilibrium is disturbed, meaning there's a change in concentration, a change in the volume of the gas, or a change in the temperature, how does the system respond to get back to equilibrium? So the goal of the system is to try to reestablish equilibrium. Again, our stresses or changes that we will see will be changes in concentration or pressure if we've got a gas, because concentration and pressure of a gas are going to go hand in hand with each other. We also will see changes in the volume of the container of a gas, and then changes to temperature. Now, you may remember doing LeChatelier's principle in Regents chemistry. Basically, it was the main thing that we did in the equilibrium unit. So when we have a reaction like this here, and if we are already at equilibrium, the system is stable, forward reaction is occurring at the same rate as the reverse reaction, and the amounts of everything are staying constant. If the concentration of a substance increases, the reaction that will reduce the amount of that substance will be favored. So one way that we talked about it in Regents is if we have too much of something, we literally move away from it. So down here, if we are at equilibrium and we increase the amount of NO, our problem is that we have too much NO, so the equilibrium would shift to the right. So we would be moving away from NO. Or in other terms, we would be doing the forward reaction because the forward reaction would consume the excess NO. So again, if we had extra NO2, then we would want to move away from the NO2. So the reverse reaction would be favored because that would use up the excess NO2. If we have extra O2 added to the system, that would favor the forward reaction. We would be moving away from the O2, we would be using up the excess O2. If we have decreased something, then our problem is that we don't have enough of it, so we have to be able to make that substance back. So we would want to move towards it. So if we have removed NO2 from the container, we need to make it back. So we would be doing the forward reaction. We would move towards it. We would be producing it because that would help us reestablish our equilibrium. All right, pressure only affects gases. So if it's that more is being added, so if we are adding more carbon monoxide, that would increase the partial pressure of the carbon monoxide and you would move away from it like we did with concentration. However, we also could have pressure applied to the system as a whole, which then would cause the container's volume to decrease. If that happens, then that will favor whichever direction produces less moles of a gas. So if we look at this example down here, we have carbon monoxide plus O2 is at equilibrium with CO2. So if the pressure of the whole system is increased and the volume decreases, then we would want to pick the side that produces less moles of a gas. So that would be the forward reaction because that would produce 2 moles and the other side would produce 3 moles. Now, if the reverse happens, if the pressure of the entire container is decreased, causing an increase in volume, then we would pick the reaction that produces more moles of a gas. Now, something else we should look at is if an inert gas is added. So if we have like this reaction here and it says that helium is added, that will not impact the reaction because that would not be a part of the K expression. So if you add an inert gas and that is not part of the reaction, that will have no effect whatsoever on the equilibrium. All right, now something big that we need to talk about. If we change our temperature, that will change the value of our equilibrium constant. That will change the value of K. So that is very important to know. Now, whether or not it will increase or decrease the value of K will depend upon whether or not it's an exothermic or endothermic reaction. So that is information that you need to know. So they would have to give you delta H or the equation with heat, or of course, lab data that told you that the temperature went up or down, and then you could determine if it was exo or endo. All right, so if we have an endothermic reaction, then heat is on the reactant side, so it would be on the left-hand side. Increasing temperature would favor the forward reaction, causing the reaction to shift to the right. So if the forward reaction is favored, that means that we would produce more product, so therefore the value of K would increase. So if we have an endothermic reaction and we increase the temperature, that would cause the reaction to shift to the right, away from the heat, which then would produce more products and less reactants. Therefore, we would see the value of K increase. If we have an exothermic reaction, then heat is going to be on the product side. So if we increase the temperature, that would cause our reaction to shift away from the heat towards the left. That would use up more products, produce more reactants, so my numerator would get smaller, my denominator would get bigger, and my value of K would decrease. So we need to be able to determine not only which way the reaction shifts, but how that would impact K when we change the temperature. So again, K is specific to temperature. So if we change temperature, the value of K will change. All right, lastly, in our example here, we increase the temperature. So here is heat. So if we have too much temperature, we will choose the reverse reaction because that would use up the excess heat. That would, if they asked us, cause the value of K to decrease because I would now have less products, more reactants. My numerator is smaller, my denominator is larger. That would decrease the value of K. And lastly, if we add a catalyst to our system, that will not cause a shift in the equilibrium. Both our forward reaction and our reverse reaction will speed up, so equilibrium will be achieved quicker, but it will not change the value of K.